Today we're going to talk about limits at infinity. This is from chapter 2.6. So all of these examples are going to be rational expressions. And they will also be made up of polynomials in the numerator and the denominator. So our first example will be this one where the highest power of x in the numerator matches the highest power of x in the denominator, okay? So in order to do this, we're going to attack this formally. Now, if you dealt with this in high school, you had more general rules to follow in order to be able to tell what the end behavior is. That is the limit at infinity. But we're going to attack this formally. And I'm going to multiply the numerator and the denominator by 1 over the highest power of x. In other words, I'm going to divide the numerator and the denominator by the highest power of x. And this will give me the limit as x approaches infinity of 6 minus 4 over x divided by 2 plus 1 over x squared. So what I've done was I've multiplied through by 1 over x squared, both numerator and denominator. And then I've simplified this into this expression. Now, there's a theorem we're going to use right now. It's an important theorem in being able to determine limits at infinity. Again, I am taking the formal approach here. And the theorem says, I'm going to put the theorem just to the right of this, that the limit of anything as x goes to infinity of c over x to the n is equal to 0, where c is a constant, any constant, and where n is a rational number greater than 0. So the theorem is to the right, and we're going to use that in each of the terms above, inside that expression, the parentheses. So when we do that, well, of course, the limit of 6 is 6, and the limit of 2 is 2, but the limit of 4 over x and the limit of 1 over x squared are both going to 0. So this becomes 6 minus 0 over 2 plus 0, which is equal to 3. That's the end behavior. That's the limit at infinity. What that means is that the line y equals 3 is a horizontal asymptote. I'm just going to refer to that as an HA. All right, so this is the first expression where the power of the numerator and the power of the denominator are the same. Now, in my next example, let me erase this. We're going to look at an example where the power in the denominator is greater than the power in the numerator. Again, they will both be polynomials. And again, most of these are going to be polynomials. All right, so just give me a second here. All right, and this one will be the limit as x goes to infinity. Of x plus 2 over x squared minus 4x. Now, once again, the highest power of either numerator or denominator is x squared. So once again, like in the other example, I'm going to multiply through by 1 over x squared, both the numerator and the denominator. Just like this. By the way, some of you might be wondering why I'm using a handheld whiteboard. Well, because in order to use the writing tablet and the whiteboard in Zoom, it just takes too much time. It's a lot easier to do it this way. So I'm going to multiply through by 1 over x squared and simplify that. And I get the limit as x goes to infinity of 1 plus 2 over x squared divided by actually I get 1 over x plus 2 over x squared divided by 1 minus 4 over x. Going to use that same theorem here. I'll show you this in a second. So as I take these limits, then I end up with 0 plus 0 in the numerator, and I end up with 1 minus 0 in the denominator. That gives me 0 over 1, which of course is equal to 0. Now, what does that mean when you end up with 0? That means that the x-axis is a horizontal asymptote. Okay, that means that this expression, the denominator is more powerful than the numerator, and this is being driven to 0, which means again that the x-axis is a horizontal asymptote. So you would be responsible for being able to tell that the line y equals 0 is a horizontal asymptote. And again, I will just call that an HA. Short for horizontal asymptote. Okay. Now there is one more variation of this, and that's where the power in the numerator is greater than the power in the denominator. Now, I'm not going to run through this entire example because basically the approach formally is exactly the same. But what I will show you is an example of this. And I would expect that you could just run through this formally yourself. Remember, on exams, you have to show all your work, no matter what. So let's take a look at the example of the limit as x approaches infinity of 2x squared plus 1 over 3x minus 4. Now, again, I'm not going to run through this entire example by multiplying through the numerator and the denominator by 1 over x squared. You should try this on your own. But what you're going to end up seeing when you do that and you finally apply that theorem, the theorem that I told you was important in determining end behavior, is that you end up with zero over, actually you end up with 2 over 0. So when you do multiply through by 1 over x squared, you end up with 2 over 0. What does that mean? That means that the numerator is growing without bound, while the denominator is going to 0. And that's considered to be infinity. It means that the graph of that function is either unbounded above or unbounded below. Really doesn't matter which it is. You could always graph it to look at it if you want to. But that is, in essence, what is going on in 2.6. So what I'll do is I have 2.7 and 2.8 recordings to make. I might put them together on one Zoom recording. But you're required to watch these, by the way, sort of a mini lecture. All right, so I'm going to stop this recording.